All right, welcome back. We're on our fourth lesson for modern physics. And in this lesson, we're going to take a step back in time before Einstein, even before Maxwell. So before we knew light was a electromagnetic wave, all the way back to Newton for a second. And all the way since we're back to Newton, hundreds of years, people have wondered what light is. Now, Newton said light is a particle. And he said it's a packet of energy, which he called corpuscles. But there was someone else at the time, Christian Huygens, who said, no, light is a wave. And they both tried to prove their point. They both had trouble proving their point, because there are certain properties where light just acts like a particle and other areas where it acts like a wave. Right? I mean, shadows form. Well, waves bend around corners. We talked about that yesterday, right? Diffraction. So why would a shadow form? It must be a particle, right? But then again, when you look through a window, some light goes through the window and some light bounces back. That's partial reflection, partial refraction. I don't know about you, but if I ever throw a little ping pong ball at a window, it only bounces back. It doesn't go through and come back. That would be really weird to see. So there are different properties where, yeah, you can explain light as a particle, and other properties where you can explain it as a wave. So at the time, they both had trouble. But of course, everyone believed Isaac Newton, because this is after he released his Principia about all the motions, and he was the most important mathematician and physicist of the time. So if Newton said it, meant he was right. All right? But there was always a goal for everyone who believed that light was a wave. I'm going to move forward. There we go. And here's the goal: to find an interference pattern. Now, if we take a double slit, and this is probably the most important experiment ever in physics. We do it at school. Sorry, we're not going to do it at home. I am trying to look for an online simulation of one, though. But there's no gizmo for it. So, let's say you take a double slit. I have like the diagrams here. Actually, I'll just use the screen. I have the diagrams. Oop. Okay, so here we have a double slit here and here. Okay, it's just two openings close together. Now, if I threw particles at those double slits, you could probably imagine that, well, some will hit this barrier and bounce back, but the ones that go through this slit will hit the wall somewhere over here, and the one that goes through this slit will hit the wall somewhere over here. And so you'll get two spots. Now, if you're doing it with light, you would expect to get two bright spots, one here and one here next to each other. Now, if you're doing this with a wave, well, your wave is going to diffract here and it's going to diffract here. And then they're going to move over each other and produce an interference pattern, similar to the complicated two-dimensional interference pattern that we were looking at yesterday, or the last lesson. And you're going to get areas of bright, dark, right? Bright, dark, bright, dark, bright, dark, bright, dark, bright. So you're not going to just get two bright spots, you're going to get multiple bright spots. And of course, this was always the goal. For anyone who believed light was a wave, the goal was to create an interference pattern. However, this was a difficult goal. The reason why it was a difficult goal is because lots of people would use candles. And they would take candles and they would hold two candles next to each other, right, and try to get an interference pattern on the wall. That is far too difficult for many reasons, right? One, candlelight is more than one wavelength of light. Two, you have two candles, and so all the different wavelengths that are coming out of it are all in different phases relative to the other. Right? To make that nice interference pattern, you need the same wavelength starting with the same phase. And nobody could do that. right? They were trying with candles. Well, then Thomas Young came up with the double-slit experiment. So his idea was to take light, and he actually used sunlight, but I mean, you can do it with you can do it with a laser, which is what we do it with now. You can do it with a light bulb, right? Anything. But he got rid of that error where you'd have light in different phases because he only used one light source instead of two. And he sent that one light source through a double slit, right? And therefore producing two waves that are both in phase with each other. And because they're both in phase with each other, he got an interference pattern. Now, since he was using sunlight, he didn't get bright, dark, bright, dark, bright, dark. He would get sort of a rainbow color, and then dark, and then a rainbow color, and then dark, because your reds would meet up in different places, forming constructive interference, than your blues would, right? And so it sort of separates white light into its colors. Okay, and this sort of proved light is a wave. We didn't yet know it's an electromagnetic wave, but it proved light's a wave. Okay, and you'd get these areas of bright, dark, which we call maxima and minima, right? Or maxima, just areas of constructive interference, and minima, areas of destructive interference. Okay, so let's analyze this a little bit more. We have our diagram here. Let's say we have source 1. Now, source 1 is just one slit, and source 2 is our other slit. And D is the separation between the slits. Now, if we go all the way down, right here, where we would get our central maxima, that's a terrible line. Sorry, I'm using a trackpad to do this. Right? There's our center maxima. Here's n equals 1. Here's n equals 2. And here's n equals 3, and so on. Okay? Now, the interesting question is, this delta x, which I've labeled as the distance between two nodal points, I have it labeled the same. But is it the same? Well, let's try. We have our example here. This equation we came up before, where sine theta n equals n minus a half lambda over d. Now, I never derived this formula for you, but this formula you can derive similarly. It is areas for constructive interference, your bright spots. But we're going to focus on areas of destructive interference, our dark spots. Okay, and I think I labeled theta n as xn over L. But I'm going to bring the L up here. All right, so here we have xn over L. Now, if we want to figure out what, say, the distance between, hold on, here's x1 and here's x2. So to find this delta x, well, that delta x will simply be this whole distance x2 subtracted by this distance x1. So if I subtract those, if I take x2 minus x1, right, I get, well, x2 is n minus a half, or 2 minus a half, which is 3 halves. So I get 3 halves lambda L over D minus x1, which is 1 minus a half, which is just 1 half lambda L over D. Okay, 3 halves minus 1 half is just 1, so we get delta x as lambda L over D. Okay, and you can do this for x3 minus 2. x3 minus 2, which would be 5 halves minus 3 halves, which again will give you lambda L over D. 5 halves minus 3 halves is 1. You can do 7 over 2 minus 5 over 2, right? Or 9 over 2 minus 7 over 2. You're always going to get 2 over 2, or 1. So all those distances are the same. So we're going to call them delta x. And we're going to use it to solve the first problem on the back of the page, where it says a student performing Young's experiment with a single color source, a monochromatic source, so a laser, finds the distance between the first and 7th nodal lines to be 6 centimeters. The screen is located 3 meters from the 2 slits. And the slit separation is 220 micrometers. Calculate the wavelength of the light. So here we have delta x equals lambda L over d. It wants us to calculate wavelength. So let's just rearrange this. So we get lambda equals delta x times d over L. All right, but what's what? Everything they give us is in units of distance, right? Units of length. So we have 6 centimeters, 3 meters, and 220 micrometers. So what's what? Now, L is the distance from the source to the screen. So let's say we have a screen, we have a source, that's L. Okay? All right. So we know that L is 3 meters. So I'm going to put in 3 meters. What's next? The slit separation is the distance between your two slits, D. Okay, so D is 220 micrometers, but I want to make sure we put everything in the same base unit, so meters. So I'm going to write 2.2 times 10 to the minus 4 meters. Then it says, well, we're left with delta x. So that would be 6, right? And a lot of students throw in 6, but be very careful. It says the distance between the first and seventh nodal line. So if this here is n equals 1, right? Let me actually zoom in. I keep forgetting to do this. If this here is n equals 1, this would be 2, 3, 4, 5, 6, 7. That would be n equals 7. It's saying that this distance is 6 centimeters. Well, that's not delta x. Delta x is the distance between any two successive nodal points. Well, how many delta x's do we have in this? We have 1, 2, 3, 4, 5, 6. So this is actually equal to 6 delta x. So 1 delta x would actually just be 1 centimeter. Or put into meters, 0.01 meters. Right? And if we do that, we will get 7.3, well, 7.33, but to significant digits, times 10 to the minus 7 meters. But usually when it comes to light, we like to write it as nanometers. So 730 nanometers. All right. Now the double slit, let me go back. Actually, I'm going to leave it here. The double slit experiment is pretty interesting, and like I said, the most experiment in modern physics. Right? Even though technically this happened before modern physics, it happened before Maxwell. It happened before before Faraday unified electricity and magnetism. But it turned out to be the most important experiment in modern physics, and we'll get to why in a couple lessons. I'm actually going to start quantum mechanics tomorrow. But there is a couple other cool experiments that I'm not going to really talk about. Your textbook talks about it if you want to read about it, but you can also do a single slit and get an interference pattern. And you can also do multiple slits, like 50, 75, 150. Those are actually called diffraction gratings, right? And they're very useful. You see them everywhere, especially in spectroscopes, right? We don't use prisms very often to split up white light. We use diffraction gratings. And if you remember in grade 9 chemistry, you looked through these tubes at different discharge tubes to see their emission spectra. Well, you were looking through a diffraction grating. That's what that is. It's just multiple slits stuck very close together. So you get a lot of light penetrating it, and it also is able to split it up into its spectra. Okay. Now, if you have like a little laser at home, I can tell you how to simulate a single slit and a diffraction grating. I can't figure out a way to do the double slit with just regular materials at home, because those double slits need to be very close together. Right? In this example, where is it? 220 micrometers. So it's hard to make two slits that are that close together. But a single slit's easy to do. If you take two pencils and wrap elastic band around them and just shine a laser in between the pencils, you will actually get to see a single slit interference. If you want to see a diffraction grating, you all have these at home. They're called CDs or DVDs. Right? Now these won't pass through, but it actually reflects off like a diffraction grating. So let me show you. I don't know if this is going to work. My first demo on video. You see the laser We can kind of see. Let's bounce this. Oh, there. It's hard to see. You can see the central maxima, which is always the brightest point, but I don't know if you can see all the other points there. Okay, but you can see sort of a pattern of light, dark, light, dark, light, dark, similar to a double slit pattern that you would see, except they're more separated apart, because when you put that many slits that close together, the slits are much closer together, and the closer you can get the slits, the more separated your pattern is, right? Delta X is larger if D is smaller. Okay, and it also will be brighter than a double slit experiment because you're getting more light energy going through. Okay, let's move on. There's another very important experiment that I want to talk about. All right, the Michelson interferometer. So let me explain this. So here we have, a laser, and this laser is going to hit, here's the laser. This laser is going to hit this beam splitter. Now what's a beam splitter do? Exactly what it sounds like, right? It's going to have part of the laser reflect off and come down this way, and part of it reflect off and come this way. Okay, so it splits the beams into two beams. One that's going to hit this mirror and bounce straight back, and one that's going to hit this mirror and bounce straight back. And when they bounce straight back, they're going to hit this beam splitter again. This one's going to reflect, right? And this one will both bounce back, but we don't care about that, and transmit through. So we get now these two beams coming back to interfere with themselves on the screen. Now remember path difference, we talked a lot about path difference. So if the path difference is 0 and the distance they have to travel to each mirror is the exact same, well then they will meet perfectly in phase with each other and interfere constructively and produce a bright spot. However, if you move one of those mirrors, right, just a quarter of a wavelength, then the path difference for one will be a half a wavelength more or less, depends which direction you move the mirror. And now they'll be completely out of phase, produce destructive interference, and you'll get a dark spot. Okay, so this is actually really cool because you can move a mirror, and as you move it, count the light going between dark, bright, dark, bright, dark, bright, dark, bright, and you can actually measure how much you moved the mirror on the order of micrometers. Right? So it's a really cool experiment. It has many, many uses, including with, if you've heard about the detection of gravitational waves. Right? I'm actually going to post a video that shows how we detected gravitational waves. And it's a huge, well, two huge laboratories which are based off of Michelson's interferometer. Okay, so let's move on. This just all explains what I just explained. That's kind of like what it will look like. And I'm also going to show you a video of someone going through the Michelson interferometer experiment. Okay, there's LIGO. This is the lab that detected gravitational waves. It's called the Laser Interferometer Gravitational Wave Observatory. Okay, so let's go through our second example. So this comes from the other formula that I put on your sheet. Let me write this. So we have lambda equals 2d over n. Okay, in this case, d is not the separation between sources. Okay, there's just one source, the laser. Okay, and there's no slits that we're passing anything through. And n, the distance the mirror moved. Okay, so d, sorry, I forgot to say, d is the distance the mirror moved. N is the number of bright fringes that you would count. Okay. All right, and the reason why there's the 2 is because we're counting bright fringes, not bright and dark, bright and dark, bright and dark, just the bright ones. Or you can count sorry, or you can count just the dark ones, right? Same thing because the spacing is equal. Now for this question we have, you visit an optical engineering house in which an interferometer is illuminated by a monochromatic source of wavelength 640 nanometers. Now you slowly and carefully move the movable mirror, and you find that 100 bright fringes pass by your reference point, because you need a reference point where you're going to count. It might be easier to actually look at the MIT video of this experiment being done, so you kind of understand what I mean by a reference point and counting the number of fringes that pass through that. So pause the video, go look at that one, and then come back and we'll work on this question. Okay, I'm assuming you've done that now. Let's move on. All right, so we're going to rearrange to solve for D to figure out how much the mirror has moved. So doing that, we get lambda n over 2. Okay, and then lambda we have as 640 nanometers, n is 100. If you multiply that all out, you'll get 3.2 times 10 to the minus 5 meters, or 32 micrometers. Okay. So make sure you look at the other videos I post. If you want to try the experiment because you have a handheld laser at home, go ahead. It's not mandatory. I am going to look for a double slit. I'm trying to look for a double slit simulation that we can do, but I haven't found one yet, so we'll see. And yeah, see you next time for quantum mechanics.